Okay, let's talk about chapter 28, which is special relativity. So we'll talk about Einstein's postulates, which are key to the theory, the relationship between simultaneity and time dilation, which is the fact that events don't occur at the same time between moving objects. Length contraction, moving objects appear shorter. I mean, they're actually shorter, they don't just appear shorter. The way we add velocities is a little bit different in relativity versus regular Galilean transformations. When things go fast, they have different momentum than mv, and then relativistic energy, which is the famous E equals mc squared plus a little bit. Okay, so the idea with special relativity is that Einstein realized that, well, there were some experiments that showed this, but he basically fully accepted it and tried to determine what the consequences of the fact that the speed of light is constant for all objects. So the first postulate, before we get to that, the first postulate here just says that the physics is the same. Physics in general is the same in inertial reference frames. What that means is, if I do an experiment here, if I go to the moon and do an experiment, if I go to Mars and do an experiment, the physics will behave the same in all those environments, as long as we are not accelerating. Our laws of physics and motion are the same no matter where we are in the universe. A non-inertial reference frame will be one where you are, for example, rotating or spinning with respect to some other reference frame, so that you would you'd have what are called fictitious forces, which are like when you turn left and everything falls off your dashboard and onto the floor. It makes you mad. Okay, that's like a fictitious force, and that would be a non-inertial reference frame. But if you're driving straight down the highway at 75 miles an hour and you never change speed, you feel no forces, you can drink your coffee, nothing spills, that's an inertial frame. If you were in that car at 75 miles an hour, you could do physics experiments and everything would behave the same. You wouldn't be able to tell whether you're moving or not if you blocked out the windows, for example, and you had a very smooth car and you didn't feel the bumps. So that's the first postulate, is that the laws of physics are the same in all inertial reference frames. So here's the definition of an inertial frame. The second postulate is that the speed of light is the same for every observer. Everybody agrees that the speed of light is the same value. The Michelson-Morley experiment was the first one to demonstrate that the speed of light is independent of the motion of the Earth about the sun, which means the speed of light as we go around the sun is not faster than the speed of light perpendicular to that motion, which is what you might expect. So that's the second postulate of special relativity, that the speed of light is constant for every observer, independent of the motion of the source. So, for example, if you're on a train driving by, you're going to measure your own speed to be 0. I'm going to measure your speed at 35 miles an hour, but both of us are going to measure the speed of light to be c, regardless of our motion. So Einstein took those two things, especially the second one, and said, okay, what happens if that's really the case? What does that lead to? And that leads to these effects about simultaneity and time dilation. Basically, things don't happen at the same time according to moving observers. The reason for that is, so we've got a moving train here. There's an example there of what's going on with a moving train. Basically, rate, the speed of light, rate times time equals distance. So in a train, if it's sitting still and you shined a light up and down, it would travel some distance d in a certain amount of time t, and it would travel at the speed of light. That's according to you on the train. Now, if you are, or if there's an observer on the train, on the ground watching you, and the train drives past, and the same thing happens, the light is actually going to trace out a triangle from the perspective of the person on the ground, because as they're moving, the thing goes up and down, but traces out a longer path because it's moving over while it's moving up, because the train's moving forward. So you can immediately see, if we both agree that the speed of light is constant in this reference frame, T1 and D1, in the second reference frame, this d prime, or d2 for example, this, hopefully everybody agrees, that distance is longer than that distance. So we have a disagreement here. Speed of light's the same, but now we have different time and different distance. And this relationship here is time dilation and length contraction. Moving distances are objects appear contracted, and time is dilated. So objects appear longer than they are or shorter, and the time is lengthened based on this effect. So this is a different example of where you have the observer on the train. If you have a blinking light, observer A is going to imagine both these rays hitting the observer at the same time. They're not going to see a time difference. But the observer on the ground, since the speed of light is constant, and everybody agrees on the speed of light, if the train's moving this way, this lady is going to run into this light beam before that one, which obviously they can't both be right, can they? And that's the thing, is that she will say they both arrive at the same time. He will say, no, this one arrived first, right? But the way it works out is that he's going to see the length being contracted to compensate for that extra or that shorter time. Okay, so time dilation is the phenomena of where time is passing slower for an observer moving relative to someone else. So people disagree about the time it takes for something. So here's this example of the light clock of the light going up and down with a certain distance, but on the ground the distance from the perspective on Earth, the distance is longer than it should be, and it's based on the velocity. The distance you travel this way depends on your speed. Okay, so this is a derivation of time dilation, and I definitely recommend you just kind of read through that and follow it if you can. It's just algebra, and it's pretty straightforward. You can see what you're getting. And then what you end up getting is this, where the time in one reference frame is equal to the time in the other reference frame divided by this factor square root of 1 minus v squared over c squared. And that's your main equations that you're going to be using. You're going to calculate gamma, which is 1 over the square root of 1 minus v squared over c squared. So notice, plug some numbers into this formula, and what you see is that if you go the speed of light, you have c squared over c squared. 1 minus 1 is 0. You have 1 divided by 0, so you cannot go the speed of light, according to this equation. The closer you get to c, the bigger this gamma value gets, and the more your time dilation is. Okay, so for most of the time, v is less than c by a lot. Usually we're only going a few miles an hour, so 1 minus a tiny number and the square root of that, and then 1 minus 1 divided by that. Your gamma is basically a negligible factor. It's almost 1 because it's basically the square root of 1 minus 0, and so gamma ends up being very close to 1 most of the time. But the fact is, time is dilated when people are moving, and people disagree at when things happen. The twin paradox is a fantastic example of relativity. If a twin goes out at a high speed and comes back, the clocks will be different. The twin will be younger. The one that flew away and left home for a little while is going to be younger. The one that stayed home is going to be older. That's not an illusion. It's a true fact. And it's because of the speed and velocity of this person moving more through space and less through time, whereas this person stays home and moves more through time and less through space. Because that's one of the things with relativity, is that space, x, y, z, and t are the same vector now. So the more you move through the space dimensions, the less you move through the time dimension. The more you move through the time dimension, the less you can move through the space dimension. So if you're just sitting still, you're actually moving through time at the speed of light, basically. So get moving, okay? You'll live longer, or at least it'll seem longer. Okay, length contraction, same thing. You get a gamma factor, there it is. The length of an object is shortened relative to the moving observer's frame, and it's shortened by that same gamma factor, but it's 1 over gamma in this case. And this is an example. If this rocket goes at a very high speed from Earth, we'd see it contracted. The person on the rocket ship wouldn't see that they were contracted, but Alpha Centauri and space and everything around them would appear contracted to them. Okay, so that's a weird thing. It's a true thing. It's not unusual. Okay, and then continuing on here, blah, blah, blah. So relativistic addition of velocities. Normally, you know, if you're throwing a ball at 1.5 meters per second and you're walking at 1 meters per second, the observer would measure that as 1.5 plus 1. You just add it up. Same thing here. In relativity, that works when you're going less than the speed of light. A classic velocity addition is just literally you add things up. In relativity, you have to include, again, this gamma factor, or it's not exactly the gamma factor because you end up multiplying it, but again, you have to add a factor that's dependent on your velocity and the speed of light, and that's the relativistic velocity addition. So if one object is this and one object is that, identify blah, you just plug everything in. Again, most of these problems in this class are just what we call plug and chug. You find the equation and plug the thing in. So it's important to understand conceptually what's going on so you can find the right equation. Okay, blah-de-blah-de-blah. Yeah, so the Doppler shift, the wavelength of an observed object will change when it's coming towards you. It'll be blue shifted. If it's moving away from you, it'll be red shifted. So you can calculate the wavelength, and it's again just a function of the velocity and the speed of light. And you can calculate the frequency, which is just you know, basically the same equation but 1 over it. And okay, and blah 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 blah. Okay, relativistic momentum, P equals mv, same thing, but now we just throw a gamma factor on there, so you're starting to see a pattern. If you want t, it's gamma t. If you want length contraction, it's 1 over gamma times the original length. If you want the momentum, it's gamma mv. In this case, we use u for the velocity, and that tells you the momentum, relativistic momentum. Again, it peaks out at speed of light, so you can't go the speed of light because then you'd have infinite momentum. And so this is what gamma looks like. So you can see why we don't normally experience relativity or relativistic effects in daily life, because not until you reach 80% the speed of light, which is super duper fast, do you even start to see the effects of gamma, and then only until about 90% the speed of light does it really take into account. So even our fundamental particles, when we accelerate them, we can only accelerate them to 99.9999999% the speed of light, something like that, 91% the speed of light, before we can't dump any more energy into them. Okay, so relativistic energy, you remember the E equals mc squared, and of course we just throw a gamma on there to get the total energy of a particle, which depends on their velocity. So it ends up being their intrinsic mass, mc squared, and their velocity combined gives you this E equals mc squared, and then there's the rest energy, E equals mc squared when V is 0. Okay, blah, 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 nuclear energy, some examples here, and again, there's your, classical kinetic energy. You could keep increasing your velocity forever. Relativistic kinetic energy, you cannot, you max out at the speed of light. That's a key point again. There's Fermilab. You've got your accelerator, your complex. This one's actually a lot smaller than that one, but the perspective is makes it look bigger. And you've got your things. Okay, so that's the total thing for relativity. So what do you care about? Do we have a summary here? Chapter 28, end of chapter. Okay, summary. So Einstein's postulates. The laws of physics are the same in every inertial reference frame. Number 2, the speed of light is the same for all observers. Those are the 2 postulates of special relativity. That allows you to calculate the effects of that if the speed of light is the same for everyone. And the 2 things are that moving observers disagree on when things happen, and that's because of time dilation. And time dilation is just, you want to know when something happens, it's gamma times what it happens at rest. And then you get the factor of what the observer calculates. Length contraction, same thing. Objects appear shorter when they're moving. Let's let's see, relativistic addition. So you can add velocities together. It's a simple equation. It looks scary, but it's not. And that is how you add two velocities together. They don't just add up like normal. The relativistic Doppler effects allow you to calculate the shift, whether it's red shift or blue shift. Tells you you put in the velocity. Either it's moving towards you, so it's positive, or it's negative, moving away from you. Relativistic momentum, something moving has gamma mv amount of momentum, not just mv. Energy is gamma mc squared. If velocity is 0, gamma is 1, and you have E equals mc squared. And that's basically it. Okay, see you guys later.